Chapter 2 of the video lecture series. Now in Chapter 1 we did the intro. In Chapter 2 we're going to look at the chemical level. And as I mentioned before, the chemical level will consist of atoms and molecules. So atoms and molecules. Here we have a lot of definitions. The first definition we have is matter. Matter is anything that has mass and occupies space. There are 92 naturally occurring elements on the periodic table. Again, atom is the smallest particle that exhibits chemical properties of an element, and there are three forms of matter: solid, liquid, and gas. Here's the periodic table, and of course 92 of these are the most occurring. Now when it comes to the exam and when it comes to biology, the most common elements are what I call CHO-N. CHO is C-H-O and then N. Now what that stands for, CHO-N, is carbon, hydrogen, oxygen, and nitrogen. I'll repeat them. So that CHO-N is a short form for carbon, hydrogen, oxygen, and nitrogen. The reason for that is because it makes up something like 98-99% of the body's composition. So most living things have carbon, hydrogen, oxygen, nitrogen. That is important for a test. Now every atom has what's called subatomic particles. So every atom has subatomic particles. They're made out of neutrons, which have no charge, made out of protons, which have a positive charge, and they're made out of electrons, which have a negative charge. Now technically the weight of an electron is basically 0. On the slide here it says 1 of 1/1800. That means basically 0 if you're using a calculator, right? 1 divided by 1,800 is always almost going to be basically 0. All right, so the subatomic particles are neutrons, protons, electrons. Now the mass, when someone says mass of an element, the mass of the element is found in the nucleus. So the mass of an element is found in the nucleus. What's inside the nucleus? Protons and neutrons. You'll see a slide in a short for that. So one more time. The nucleus of an atom is made out of protons and neutrons. That makes up most of the weight. The electrons are the ones that are going flying around in what we call orbitals. And that's mentioned at the very bottom of the slide. Orbitals. So electrons fly around in orbitals. Okay. The next thing we have is that everything on the periodic table has a chemical symbol, like carbon is C. Everything on the periodic table has an atomic number. And the atomic number is the same as the number of protons. So it's the same as the number of protons. Then every element on the periodic table has a mass called the average atomic mass. And a moment ago I told you that the atomic mass is based on the nucleus. And the atomic mass nucleus is based upon the mass of the protons and the neutrons. So this is the kind of math that you're likely to come across on a test. We've already said that the proton number is the same as the atomic number. So the proton number is the same as the atomic number. Then we have our neutrons. Now the neutrons are related to the mass, but it's really the atomic mass minus the atomic number. Because remember, we said that what two things make up the mass? The protons and the neutrons. And if we want to find the neutrons, then what we do is we take the mass, we subtract the atomic number, which is basically the number of protons, and that's going to give me the neutron number. So in this case here, the author is using sodium as an example. The mass of sodium is 23 grams. We're subtracting the atomic number of sodium, which happens to be 11, which gives us the neutrons for sodium to be 12. And of course, as long as the atom is neutral, the electron number and the proton number will be the same, as long as it is neutral. So if the charge of the overall is 0, neutral, then the number of electrons and the number of protons is the same. Okay, here's a good example. In this picture, we have 8 protons inside, we have 8 neutrons inside, and we have 8 electrons flying around. Now, if we were to go back a couple slides, which I will in a moment, is I'm going to look for 8 protons, because the protons make up the atomic number. So if I go back a couple slides, okay, so I'm going to go back a couple slides, and I go to this one. So I'm looking at the number of protons being 8. And if I look up here in the picture, I see that oxygen in red has 8 protons. How do I know? Because that's the atomic number that's listed at the very top. You can see it with the legend here. And I'm looking for 8 because the example I was on showed that I had 8 protons. So that means I'm dealing with oxygen. The mass is 16 because the mass is always going to be protons and neutrons put together to make 16. So if I go back to the slide we were on, which is this one, this example here is really of oxygen. Okay? Neutral oxygen, because it has 8 protons. It's got 8 neutrons for the mass to be 16. And of course, since it's neutral, the number of protons and the number of electrons must equal. So this example is really of oxygen. Okay, now we can move forward. Okay, now we have isotopes. Now the magic thing about isotopes is it's the same element. So in this example, it's carbon, carbon, carbon. It's the same element. Notice, because the protons are the same for each, 6 protons, 6 protons, 6 protons, the atomic number will also be 6 because that's how we identify the element on the periodic table. So carbon is carbon because it has the atomic number of 6, which is the number of protons, which is also 6. Now what about the electrons? Notice the electrons are the same for each of these because this is still considered neutral. No change in the charge. Since there's no change in the charge, the number of protons and the number of electrons for each of these will remain the same. What has changed is the number of neutrons. Because the number of neutrons is now different between 6, 7, or 8, I can now say that we're dealing with isotopes, where it's the same element, but the only thing that changed was the number of neutrons. So I changed the number of neutrons. Likewise, as a result, I have also changed the atomic mass. Because as I said, the mass is always protons and neutrons put together. So why is it called carbon-12? It's called carbon-12 because of the 6 protons, 6 neutrons. Why is it called carbon-13? Because I have 6 protons and 7 neutrons. And why carbon-14? Because I have 6 protons and 8 neutrons. In a isotope, the two things that change in an isotope are the number of neutrons and the mass. So when the number of neutrons change, the number of mass or the mass changes, then we call that an isotope. So it's a variation of the same element, but the number of neutrons and therefore the mass has changed. Okay, don't care for this. Okay. This rule is important. This is a basic chemistry rule called the valence shell. The valence shell is the outermost shell that electrons fly around in. So in the previous picture, we saw electrons flying around on the outside of the nucleus. Well, the outermost shell is called the valence shell. Now, why that shell is important is because that is what is either going to lose electrons to something else or gain electrons from something else. Now, the ones that are called noble gases or inert gases are the ones that have the outermost shell already filled. Now, why is it called the octet rule? As you can see from the title there, the octet rule is because the outermost shell typically carries 8 electrons. So unlike helium, which only has 2, but everything else beyond that, all the others you'll see in a second, all of those beyond that have 8 in the outermost shell. That's why they're called inert noble gases. They tend not to react with anything. Okay? So if you have all 8, like helium, neon, and so on, then they're chemically inert. They will not react. That's why you have helium in your party balloon and not hydrogen. Hydrogen only has 1 electron in the outermost, and it's highly reactive. So if you know anything about history, you had the Hindenburg explode. It was a blimp. It's like the Goodyear blimp, but it was not filled with helium. It was filled with hydrogen. And when it popped, it reacted with the outside air, the oxygen, and it exploded. And that's what a hydrogen balloon would do when it reacts with air. It will explode. Now, if I go back, you'll see that if I go back to my periodic table, the ones in the far right, so helium, and you should be able to see the far right now, helium, neon, argon, krypton, xenon, radon, all of these are part of the noble gases or inert gases because they don't react with anything. And by the way, if you wanted to figure out which ones were which, the way you do it, you simply read the column. The first column has only 1 electron in the valence shell. The second column has only 2 in the valence shell. So column 1 would be 1, column 2 is 2. You jump over the Grand Canyon, and now we have 3, 4, 5, 6, 7, and of course the last column being 8, being the noble gases. Okay, going back to where I was. So here's another version of the author is providing. Here I see the same thing. The first column, notice if I have the little yellow ball, notice there's only 1. Because we're in the first column, it only has 1 in the outermost shell. The second column only has 2 in the outermost shell. Go jump the Grand Canyon, and then I have 3, then 4, then 5, then 6, then 7 the outermost, and so on. And that's why it's important to know how many electrons you have, because if you've got 1 to give away, then you're likely to easily lose the 1. That means you're going to be very reactive, like hydrogen is. If you're on the other side with fluoride or fluorine here and chlorine here, they have 7 and they only need 1, so they're likely to most likely gain electrons. Now, why that's important is because a lot of it has to do with the losing, the gaining, or the sharing of electrons. That's how elements are put together. Elements are put together by either losing, gaining, or sharing electrons. Okay, next slide. Now, we're going to have different kinds of compounds. Now first you need to know what an ion is. An ion is a charged element. So an ion is a charged element. So if I had hydrogen by itself, just one H only, then it would have a +1. And that means it's now charged. It's got one electron in the outermost. It's charged. Okay. Chlorine. If I had chlorine by itself, just a plain old Cl, it's going to have 7 in the outermost, but it's going to be called -1 because it needs just one more to be full. So it's going to be called -1. So things on the left side of the periodic table tend to be a plus in terms of positive ion. Things on the right-hand side, not counting the very last column, things on the right-hand side tend to be negative because they are a negative ion. But they are, again, charged negative. So here's an example of why it's a positive. So potassium is in the very, very first column. Potassium is a +1 because it's ready to give away one electron. So atoms that are positively or negatively charged are called ions. Okay, so positive, negative charge, ions. Next slide. So again, these are examples of all of these are positive. So sodium is in the first column, so +1. That's why I see only 1 there. Potassium is also in the first column, so +1. Calcium is actually in the second column of the periodic table, so it's a +2. Magnesium, +2. And as I said earlier, hydrogen was a +1 because it's in the first one. So these are now all the positively charged ions. Now, before I go any further, you need to know what positive charged ions are called. They're called cations. C-A-T-I-O-N. So cation. Some people pronounce it cation. It's cation. C-A-T-I-O-N. Cation. Okay, on this picture here, we see the negative ones. I mentioned chloride. Remember I said it's very close to the last column on the periodic table. So it has 7 electrons. It only needs 1. So it's going to be a negative charge. We have more complex things that are also negative charge. So the bicarbonates are a -1 because you see a -1 there. Phosphates are a -3 because you see a 1, 2, 3 slots are missing. So 1, 2, and 3. So -3. So these are negative charge. Now negative charged are called anions. A-N-I-O-N. Anions. Okay, those terms are now available to you on this slide. So as you can see, sodium wants to lose electrons. So sodium wants to lose electrons, and therefore they're called cations because they have a positive charge and they want to lose 1. Now remember earlier I said that normally you would have the same number of protons and the same number of electrons if it was neutral. Well, notice that's not the case here. So when it comes to ions, the protons and the electrons will not match. So when it comes to ions, protons and electrons will not match. Why do I have a +1? Because I lost 1 of the electrons. That's why it's a 10 and not an 11. Okay, so that's important to remember. So it's going to be 11 protons for sodium because that's the atomic number. Sodium's atomic number is 11. Therefore, it's got 11 protons. But this time, because it's an ion, it's not going to have 11 electrons. It's going to lose 1, so it's going to be 10 electrons. Okay. The opposite is for the anions. Here I have chlorine. Normally, chlorine has 17 protons because the atomic number of chlorine is 17. So 17 protons. As I said, normally it would also be 17 electrons too if it was neutral. But because it's an ion and it's a -1, is going to gain an electron. So anions will gain an electron. That's important to remember. So let's refresh that. So the positive ones are +1. They're going to lose electrons. So cations lose electrons, right? So cations lose electrons. Anions gain electrons. That's why it's not 17 electrons here. It's 18 because the charge is -1. It gains one more. Okay, next. Okay, I don't care for that. Okay, beyond the scope of our class. Okay, now this is important. These are the kinds of bonds that we form. Bonds are how we join elements together. So I've got an element called sodium, and I've got an element called chlorine. And these two elements are going to be joined by, in this example here, ionic bonds. Ionic bonds. That's because we're going to have a loss or gain of electrons. So in an ionic bond, ionic bonds are a gain and loss of electrons. That's important. That's what this slide is getting at. It's a gain and loss of electrons. Sodium is going to lose the electron, and chlorine is going to gain the electron. Very, very important. Next slide. And it shows it nicely in this picture. Every textbook has this picture. So here you see that one lone electron going dot, 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 dot over to chlorine because it was missing one to be happy. And as a result, these two are held together now. Sodium is now held on by chlorine. These two are attached, and the attachment is an ionic bond. Okay. The next kind of bond we have is called covalent bond. This is a sharing of electrons. Typically you see this in what's called hydrocarbons. Hydrocarbons. Like your gasoline, for example, is a good example of hydrocarbons. So anything that deals with carbon typically will be a covalent bond. Not always, but typically it will be a covalent bond. Okay, all right, next example. Next slide. Okay, this is a good one. As you can see here, we have carbon dioxide, and this would be a covalent bond. Okay, a covalent bond. Now the next term I want you to be aware of on this slide is the word isomer. An isomer is the same chemical formula. So same chemical formula. But they come in different shape. And that different shape gives it a different function. Remember I said earlier in chapter 1, by changing the structure, you change its function, right? So here I have the same chemical formula, but because the arrangement is different, it's going to be different, and it's going to act different. Same formula, but it's going to look different, and therefore it's going to act different. Remember, the anatomy affects the physiology. So here's a good example of all of these down here at the bottom. I've got glucose, I've got galactose, and I've got fructose. Notice, same molecular formula. They all have 6 carbons, 12 hydrogens, and 6 oxygens. But because they are arranged differently, this one looks like a pentamer. These two look a little bit similar, but they don't have the exact same structure. And because of that, they are isomers. And because they are isomers, our body doesn't necessarily treat it as the same thing. They have different shapes, different structures, therefore different functions, even from a biology point of view. Okay, all right, so let's make sure we're clear on the word isomers there. Okay, so far what I've done is a chemical bond. The first chemical bond was an ionic bond. That's the first one I did. that's held together with either gaining or losing electrons. The second one that we were on a moment ago was covalent bond. And then I mentioned isomers that belong to this covalent business, the isomers. Okay, and most of these, remember I called these out earlier to you. I said CHO-N, that was carbon, hydrogen, oxygen, nitrogen. They're primarily held together by covalent bond. Okay, so they're primarily held together by covalent bond. Okay, we can have a single covalent shown by one stick. I'll show you what that means in a picture in a moment. So single covalent will be one stick, double covalent will be two sticks, and a triple covalent will be three sticks. Let's look at a picture of that. So here I have a single bond with one stick. Now, by the way, that one stick actually represents 2 electrons. So one stick represents 2 electrons. Then we have a double bond. So I have 2 sticks here, which now represents 4 electrons. And then I have a triple bond down here, which are 3 sticks, which represents 6 electrons. Okay, so be aware of that for the test. Okay, so single bond, 1 stick, 2 electrons, double bond, 2 sticks, 4 electrons, triple bond, 3 sticks, 6 electrons, because each stick represents 2 electrons. Okay. So again, covalent bonds are shared electrons. Shared electrons. Okay, now this is important. So when it comes to a carbon skeleton, we have a straight chain, a branch, or a ring. Now, why does that matter? Well, if you ever go to the gas station and fill up your gasoline, remember I said gasoline is a good example of a covalent bond. When you fill up gasoline, you got a choice between the regular unleaded, middle unleaded, and then supreme, premier, or whatever unleaded. And each one has a different octane number. So you have an 89 octane, and I guess the best is 93 octane. Now, the reason why that matters for certain engines is because they're designed to work with a better quality fuel. 93 octane, which is the higher premium gasoline, will result in a more cleaner burning fuel, giving you better gas mileage and giving you less engine knocks when it comes to sparking your engine to actually burn the fuel. If you keep filling up with cheaper gasoline, the 89, sometimes you find that that's a problem where you have stalls and things like that with your engine because it doesn't burn fuel efficiently. That has a lot to do with these chains. So whether it's a straight or a branched or a ring. Now the other thing is a ring is almost always kind of thing, aromatic. So your perfumes, if you were to do a chemistry on your perfumes, anything like flower smell or whatever, it's actually going to be aromatic. And by aromatic, it always implies an aromatic ring. So certain smells, if you have smells and scents, it's because it's aromatic, and they're called aromatic rings. So if you know that you have perfumes, you're probably going to have a ring structure in the perfume. Okay, next structure, next slide. Okay, now comes negativity, electronegativity. Electronegativity deals with how well that element can pull electrons. Now the rule of thumb for electronegativity is the further right you go on the periodic table and the further up you go on the periodic table, the more ability you have to pull electrons. So let's go back to our periodic table real quick. And in our periodic table, let me go back to the right one. Here it is. If I go to the right, the electronegativity increases. If I go up, the electronegativity increases. So fluorine has the highest electronegativity, which means it has the greatest ability to pull electrons. So like hydrogen fluoride, for example, would be very, very reactive. Hydrogen chloride would be pretty reactive as well. So as you go from left to right and from bottom to top, the more electronegative you become. So fluorine would be the most electronegative. They would ask something like that on a department exam. So far right and far up tends to be the most electronegative, the ability to pull more electrons. Next slide. Okay. Alrighty, and I've said this to you, so I'm not going to show it to you. Electronegativity increases as you go from left to right. That's what I said earlier. And it also increases as you go from bottom to top. So fluorine would be the most electronegative. Now, do you have to memorize the periodic table since I keep going back to it? No. If they ask such a question on the department exam, then it will be provided to you as a reference or some mini form of it available to you. Okay, so you don't have to memorize that. You do need to know the trend, so you will have to memorize the trend. All right, so be aware of that for the purposes of the test. Again, left to right, more electronegative, and from bottom to top, more electronegative. Okay, don't care. Okay, now comes to nonpolar. Now, so covalent bonds can be polar or nonpolar. Now, nonpolar are basically just plain old covalent bonds. So I don't know why books often say that, but just be aware that when someone says plain covalent, a plain old covalent or plain covalent would be nonpolar. Then the other variety is polar covalent. And the best example is the one that you see on the slide, water. Water is a polar covalent molecule, H2O. Okay, so water is polar covalent. Very important for a test. So water is polar covalent. And then again, down here it says carbon dioxide. Well, this is nonpolar. It's just basically plain old covalent. So just be aware of that. This is just another way of saying just covalent. It's only water that's unique as a polar covalent. That you need to know for the test. Okay, now this term. This term does not only apply to water, but it applies to many things. Like for example, the author provides one that's good for a test, and that's phospholipid. Now you don't know what that is yet. You will in a future chapter. But these are amphipathic. Now Nemesh's definition is this. Amphipathic is any structure that has two different ends with two different functions. So let's take a pencil. One end of the pencil you write with. The other end of the pencil has the eraser where you erase with. So a pencil would be defined as amphipathic. It has two different ends, both serving two different functions. Water is also amphipathic, and we'll see why in a little while. And so is this example here, phospholipid. Phospholipids are also amphipathic. One end has one characteristic, the other end has a different characteristic. Okay. All right, so these are good examples. Here's a phospholipid mentioned by the author a moment ago. This end down here is a fatty acid, so it's oily. So this bottom part's oily. And then the polar part up here is attracted to water. And that's why since the back up. There you go. Since the polar part up here is attracted to water, that's the polar part. This down here is nonpolar, and therefore it's attracted to the fatty side. And since one side likes water and one side hates water, right? One side likes, one side doesn't, that's why it's called amphipathic. Okay, that's how it works. Here we have water. Up here at the top, we have water under polar, because water tends to be polar. Okay. Then we have nonpolar. So all of these things here are nonpolar. Now, one of the things you never want to do is try to mix a polar with a nonpolar. You know that oil and water don't mix, right? Well, why does oil and water not mix? Because water is polar. Remember, we keep saying that. Water is polar. But the oil is nonpolar. So they don't attract each other. They actually dispel each other. That's why when you have oil and water put together, you're going to have, and you shake, 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 and you let it settle, that container that has oil and water in it is eventually going to break up into two nice layers. That's why. Okay? Because oil and water don't mix. Polar and nonpolar will not mix, will not blend. Okay, next slide. That's important. Okay. Now this slide's important here about different bonds. So make sure you look up this slide here in your lecture when you're watching this video. So we have one kind of bond that's a hydrogen bond. So one kind of bond which is a hydrogen bond. You will need to know the features of a hydrogen bond. That's important. Now, hydrogen bonds are often found with water. So hydrogen bonds are often found with water. And you can see it right here. Water dealing with hydrogen bonds. Now, hydrogen bonding, even among water, so even between the water, that is what allows for all the different properties of water that we're going to see in a little while. So water has a lot of properties, and all the properties of water are because of hydrogen bonding. Okay, so all the properties of water are because of hydrogen bonding. Okay, the next kind of bond are van der Waals. So be aware of those, van der Waals. And then the last one down here are the hydrophobic interactions. Okay, the hydrophobic interactions. So these are the three attractions to be aware of. We've got the hydrogen bond, we've got the van der Waals, and we have the hydrophobic interactions. Okay, so be aware of those. Now, for some of you that don't know this, Rain-X is a product that you put on your windshield, and especially if your wiper blades are not that good. And what it does is it forms a little film just on the top of the surface of your windshield. And when it rains, instead of the water blurring, the rainwater blurring your windshield, it just beads off. You can do that with a bar of soap as well. Just put a little bit of a edge of a bar of soap, rub the soap all over the windshield, then take a nice little terry cloth and just wipe off the excess, and watch, it does the same thing. It ensures that your wipers don't have to work as hard, and you get a nice little thing because of the hydrophobic interactions between the rainwater and the soapy film that you left on the windshield. So that's where the knowledge comes in. I do that same thing for the shower. So if you want to avoid having your shower fog up, the shower mirror fog up, well, you can do that on your shower mirror. Just rub it down with soap, wipe off and buff off the excess, and watch, you will not have your shower mirrors fog up. Okay, so that's how it works. Okay, now we're going to go to water. And remember I said water's unique properties are because it is polar. So polar for water. Now if you look at water carefully, it looks like a bent shape. So that's a hydrogen, and an oxygen. If you look carefully, you'll find that the hydrogen of one, so this is one water, so the hydrogen of one is attracted to the oxygen of the other. That is what this paragraph is saying right here. So the oxygen is attracted to the hydrogen of the other water molecule. That is your hydrogen bonding. Okay? So one more time. The hydrogen of one is attracted to the oxygen of the other. And that is what forms the hydrogen bonds. And that's part of your polar covalent molecule. The hydrogen side is positive. The oxygen side is more negative, and that's what makes it polar. Now we've already come across this. We have three phases of water. We've got the gas, which is basically the water vapor. We have the liquid water, and then we have the solid water, which is ice. Okay? And this is all playing a role because of hydrogen bonding. Okay? These are the other things that we have that water can do. It can transport, it can lubricate, it can cushion, it deals with waste. So these are other functions of water. It is important for a test. So transports, lubricates, cushions, and eliminates waste. Okay? Now these are now the additional properties of water that you're very, very likely to get on a test. The first one is cohesion. That's where water is attracted to itself. So one water molecule attracted to another water molecule. So if you had put a drop of water on a penny and then put another drop of water on the same penny nearby, when you move the penny and the two water drops touch each other, they become one big drop. That's cohesion. So how one water molecule is attracted to another water molecule. Then we have surface tension. Okay. That's how insects, for example, are able to walk on water because they're actually not breaking through the nice bond that holds the water together on the surface. This is going to be important later in A&P 2, for example, because that's how our lungs operate. So we have cohesion and we have surface tension so far. The next one is adhesion. When water sticks to a surface, like how water drips down the side of your container. So if you have a really, really cold drink on a hot day, and then you have condensation form on the side of your glass, and you have the water going down the side of your glass, that's adhesion. Water sticking to some substance, like a glass, for example. Now, all of these so far, cohesion, surface tension, adhesion, all of them are because of hydrogen bonding. So all of them are because of hydrogen bonding. Next slide. Okay, we continue. We have now specific heat. Okay, specific heat is also because of hydrogen bonding. Okay, that's why water likes to stay water. Let's take an example. If you want to make spaghetti, you have to heat up a pot of water. Right? To make spaghetti, you have to heat up a pot of water. If you turn it on and you let the water start to boil, okay, what's happened? The water's turning into steam, right? It's getting hot. Well, if you turn the gas off, right, you take the stove off, does it instantly cool down to plain water again or cool room temperature water again? No. It takes a lot of heat to be released before it comes back to normal plain water again, right? Room temperature water. Okay? Right? It also is not going to heat up instantly either, right? It's going to take a lot of heat to go in before you start to see that water start to boil before you put the spaghetti in. So it takes a lot of heat for it to be released and a lot of heat to go in to change 1 gram of water by 1 degree Celsius, and that's what specific heat is. And water has a very, very high specific heat. If you are a true biology, chemistry, or physics fan, there's a book called the CRC Handbook. It actually has a value for water specific heat, and that value is very, very high. Many things on the planet have low specific heat, but water is one of the highest. Next slide. Heat of vaporization, I don't really care for. Okay, these three terms you'll need to know. They are solvent, solute, and solution. So solvent, solute, and solution. Let's define them. Solute would be the, let's take an example. Solute would be the food coloring powder. So if you're having Kool-Aid mix, for example, the Kool-Aid mix, the Kool-Aid powder would be the solute. Water would be the solvent, because that's what's doing the dissolving. And then when you have the solute into the solvent and it's finally dissolved, then we call that a solution. So solute is what's being dissolved. So solute is what's being dissolved. Solvent is doing the dissolving, and solution is your end product. Very, very important, almost always asked on a test. Okay. Now remember we said that water is polar, right? Water is polar. Okay. Now why is that important for us? Water is a universal solvent. You dissolve a lot of things in water. This COVID-19 vaccine that's being shipped around the planet, well, that COVID-19 vaccine actually comes in a dry form that's frozen. And then when they actually want to give it to somebody, they have to put pure, clean water in there and reconstitute it, shake it, and then give it to someone. I've actually seen it done when I had my flu shot given, where it was a dry powder form in the little vial, and the pharmacist had to add liquid to it, distilled water basically to it, and then mix it and then give it to me. Well, the same way here. Water is a universal solvent. It has a polar quality and it has a nonpolar quality, and therefore that's why water is a universal solvent. So it's got a hydrophilic end, which loves water, and then it's got the hydrophobic end that hates water. Right? So hydrophilic, hydrophobic. There you go. The other end of water is hydrophobic, which is the nonpolar end. So let me say that one more time. Water is a universal solvent because it has one end that is polar, which is hydrophilic. So one end is polar. Right, let me go to that slide. So one end is polar, which is hydrophilic, and the other end is nonpolar, which is hydrophobic. And that's why things can tend to dissolve in water if whatever you're dissolving likes to be dissolved in water as well. Okay? So hydrophilic, hydrophobic. Now what can I say about water because of this? Because one end is hydrophilic and the other end is hydrophobic, I can use that word we saw a moment ago called amphipathic. So water, the phospholipid example, they are amphipathic, just like that pencil example. Okay, there's my word, amphipathic. So water is amphipathic, just like the phospholipids are amphipathic. And there it is, by the way, again, too. The author restated it, too. So phospholipids are amphipathic. Water, because it's both polar and nonpolar, is also amphipathic. And only things that have a amphipathic quality can dissolve many other things. Here's a picture version of just that. So here is a glucose molecule in water, and notice it nicely dissolves it. Here is a salt going in, forming a little shell. This picture is of value to you. So this picture is of value. Make sure you make a note of it. So here I'm forming a hydration shell of this type, and here I'm forming a hydration shell of this type. This will allow me to completely dissolve it, whereas here we're not really just dissolving it, we're actually breaking it apart. So here we're not doing that. Glucose, if you put sugar in, now when I say sugar, I'm talking about glucose. If I put glucose in water, it just dissolves, but it's still chemically one thing. See how it's still chemically glucose? Let me restate that so that we're all together. Right here, I have a non-electrolyte, okay? That's glucose. When I put glucose in, it will dissolve it. It says it right there, it dissolves. But chemically, glucose still stays glucose. That's not true for ionic things down here. So when it's ionic, okay, when it's ionic and it goes in, it actually splits it apart. It's no longer table salt. It's sodium by itself and it's chloride by itself. That is a very big deal. And remember, glucose is a covalent thing. So covalent things tend to stay chemically intact. Right? Glucose is covalent. So covalent things in water stay chemically intact. Whereas ionic things are chemically broken apart. Okay, so ionic things are chemically broken apart. So picture A is important for that purpose. Then picture B here is something I've already mentioned about oil and water. And notice you see the oil and water where they don't mix. Because oil is nonpolar, water is polar, and it's going to leave a nice film. And it will not dissolve. Then down here we see that we have something amphipathic, and it's going to have a way to partially dissolve in water. Okay, next slide. So this one's important. Okay, now comes acids and bases. Now, what you need to know is that I have provided a separate supplement to acid and base. So I've provided a separate supplement video for acid and base. So make sure you watch that as well. So a separate supplement video has been provided for acid and base. Now before I go any further, I need to let you know what a buffer is. A buffer is any chemical that ensures that the pH does not waver too much. The pH typically goes from pH 0 to pH 14. 0 up to 7, but not including 7, is acidic. So 0 to 7, but not including 7, is acidic. Greater than 7, and not including 7, is basic. So greater than 7, not including 7, is basic. Now what does it mean when people say pH? We're measuring the hydrogen ion concentration. That's what we're really measuring. We're measuring the hydrogen ion concentration. So the more acidic something is, the more acidic means it has more hydrogen ions. It also means that the pH will be much lower. Now there are certain pHs I want you to memorize, and these are the ones you need to know. Your stomach acid is pH 2. That's important for a test. So stomach acid is pH 2. Your mouth is pH 6. So mouth pH 6. Pure water is pH 7. So pure water is pH 7. And the last one you need to know for a purpose of a test is blood. Blood's pH is 7.4. I'll repeat all of them one more time. So the stomach is pH 2, mouth is pH 6, plain water or pure water is pH 7, and blood is pH 7.4. Again, don't forget to watch the video on acid base provided as a supplement. Okay. Again, I'm skipping all of this because it's on the supplement video. Okay. Again, this is information. Now you will need to know the pH. So the pH scale goes from 0 to 14. Pure water is pH 7. You will need to understand the log scale. You don't have to do any of the heavy math, but you will need to know the log scale. This is what I mean by the chart. So this is what's explained well in the lecture supplement. Okay, so this slide's mentioned in the acid-base supplement. This chart is not something you want to memorize. So you don't have to memorize this. Only the ones I've given you, which I said stomach acid was pH 2. Pure water is pH 7. Blood is 7.4. And the mouth is about 6. And that's why I gave you 6 right there. All right, next slide. I've already given you the definition of buffer. It is something or anything that ensures that the pH does not waver, so you don't change too much on the pH scale. So that's why aspirins are sometimes buffered to ensure that it doesn't cause stomach acids to go too high. Okay, the next term that you're going to see are mixtures. So you're going to need to know the 3 forms of mixtures. So the 3 forms of mixtures. Examples provided on the slide are important for a test. So the first one you see is suspension. And notice blood is a very good example of a suspension. So blood, suspension. Colloid. Colloid would be like, to me, colloid's very much like mayonnaise. So mayonnaise. So mayonnaise would be like colloid. Okay, the next one is a solution. So a solution. Okay. So let me back up for a second. So you have suspension, colloid, solution. The information on these slides are of value to you. So these 3 bullets for suspension, these 3 bullets for colloid, and these 3 bullets for solution are important for you on the test. Here's a picture version. Many books have this. So here's a picture version of those last few slides. Okay. So you can use the picture version as well. This is one that I would suggest putting on a flashcard. Okay, don't care. Don't care. Don't care. Don't care. Okay, this one they might ask you on a test, a simple definition question. What is a mole? A mole is 6.022 times 10 to the 23rd atoms, ions, or molecules, or basically anything. Okay, so they might ask you that. Okay. Here we have lipids, carbohydrates, nucleic acids, and proteins. Okay. So these are the 4 organic biomolecules: lipids, carbohydrates, nucleic acids, and proteins. We're going to look at each of these one by one. So we're going to start with hydrocarbons. I've already mentioned that earlier to you with gasoline. Gasoline is a good example of a hydrocarbon where you have the carbons attached to hydrogens. That's why they call them hydrocarbons. They are nonpolar. They are hydrophobic. That's why oil and water, or gasoline and water, do not mix. Okay, I don't care for that. We've already talked about isomers earlier. Now we have something called polymers. Now, this slide right here is notice it says carbohydrates, nucleic acids, proteins, pretty much any of these. Now let me go back for a second here. When I looked at this slide right here, and it says 4 classes of organic biomolecules, I'm actually going to call these nutrients. These are all nutrients. Lipids are nutrients. Carbohydrates are nutrients. Nucleic acids are nutrients. Proteins are nutrients. So all of these nutrients are made of simple blocks called monomers. So a single block of something is called a monomer. 2 of them together are called a dimer. And many put together are called a polymer. So these three terms I gave you, monomer for a single unit of something, a dimer where two of them are put together, and a polymer where many of them are put together, these terms apply to all of these. They apply to carbohydrates, they apply to nucleic acids, they apply to proteins and things like that. So these terms, monomer, dimer, polymer, apply to all of the nutrients. Okay, now, how do I work with nutrients? If I take a single nutrient, a monomer, another single nutrient, another monomer, and notice I am removing water. Since I am removing water, it's going to put it together and form a dimer. Now that process is called dehydration, and some people call it synthesis. So on a test, some people will call it dehydration, some people will call it synthesis. And what we're doing is we're removing water. So by removing water, we form a dimer. That's true for all of those nutrients I called out a moment ago. True for nucleic acids, true for proteins, true for carbohydrates, even true for lipids, even though it wasn't mentioned on that last slide. Even true for lipids. Okay. So all the nutrients are put together by dehydration, synthesis, where water is removed. And in this example, we're only forming a dimer. Now what about the opposite direction? In the opposite direction, I have something already put together and I add water. By adding water, that is called hydrolysis. So by adding water, that's hydrolysis. You're going to break it apart. So this dimer here, it could be any of those nutrients I spoke of. That dimer is going to be broken apart by adding water through hydrolysis and breaking it up into its pieces. Okay, and that too is true for all of the nutrients. So anytime we see a chemical reaction that involves breaking it down, that's going to be through hydrolysis. Anytime it involves putting things together, that's going to be dehydration, synthesis, and we're going to remove water in that case. So this slide is of value. Okay, now the author starts off with lipids, so I'm going to go in that order. Now, lipids are insoluble. We already know that. They do not dissolve in water. They have four classes here. I'm only going to be talking about the first three. I don't care for the fourth one. So number 1, number 2, and number 3 are the ones we're going to talk about in the next few slides. All right, here we have triglycerides. Triglycerides are your energy storage form. So triglycerides are your energy storage form. Okay? So your energy storage will come in the form of triglycerides. Okay? Now, remember I said, how do I join them together? I join them together through dehydration, synthesis. That's true for any of the nutrients. What is a triglyceride? A triglyceride deals with a glycerol and 3 fatty acids. So we'll see that in a picture form in a moment. So glycerol and 3 fatty acids make up a triglyceride. So as you can see, the main function tends to be energy storage. Okay. And the first one here is structure. So it says most common form of lipid in living structure. So if I were writing these PowerPoint slides, I would say this. Triglycerides, this first line right here, most common form of lipid in living structures, that's going to be your cell membrane or phospholipid. So cell membrane phospholipid. So you could say that over 80%, and again, you don't have to memorize that percentage, but 80% of the cell membrane or plasma membrane, 80% of it is phospholipid. That is why that line is there. The most common form of lipid in living things. Well, if 80% of the cell membrane or plasma membrane is phospholipid, then you know it makes up most of the living cells, right? That's important. And the second one was storage in the form of fat. That's what triglycerides are. Form of storage fat. So does that make sense? So first one again, 80% of the cell membrane is phospholipid. Therefore, it's definitely fat. And it's an energy storage form. Then down here, I've got glycerol and 3 fatty acids. And again, all nutrients are put together through dehydration synthesis. Okay. Now, lipids come in, or these fatty acids come in different setups. If it's a saturated lipid, saturated lipids do not have any double bonds. They're all single bonds. So saturated lipids are all single bonds. So saturated. So when someone says I'm eating a saturated oils are single bonds. Unsaturated have at least one double bond. And polyunsaturated have 2 or more double bonds. Now, what's the problem? Well, saturated oils, because they do not have any double bonds at all, saturated oils tend to be a solid at room temperature. So, your Crisco, your vegetable shortening, those who cook with Crisco, your vegetable shortening is a saturated oil. It is a solid at room temperature. Whereas unsaturated or even polyunsaturated, because they have double bonds, they tend to be liquid at room temperature. That is important for a test. Okay, now here we have a picture. Every textbook's got a picture like this. So here in the pink, I have my glycerol. That's the pink glycerol. Then over here are the legs, which are the fatty acid chains. If I had only one, it would be called a monoglyceride. If I had two, that would be a diglyceride. And in this picture, I have all three, so that's called triglyceride. Notice I have a double bond right there, which means that this one is a unsaturated, whereas this one has only single bonds. Right? I think so. Yep, they only had single bonds. So this one is saturated. And this one does have a double bond. So this one is unsaturated. Okay. Now, what is the big deal about saturated, unsaturated, other than that double bonds make it more of a liquid and the single bonds make it more of a solid? Well, the thing it has to do with rigidity, with flexibility. So if it has a double bond, it's more flexible. If it has only single bonds, making it a solid, then it's less flexible. And that's what that's about. We also see that I'm doing what? I'm joining a glycerol to a fatty acid by our process of removing water, which we've already learned. If I remove water, that's going to be called dehydration synthesis. If I went the other way and I want to split it apart, that would be hydrolysis, which is breaking it down. So some stuff that we've already learned. Okay, so that last slide dealt with the triglycerides, your energy source when it comes to fats. Okay, now we have phospholipids. I've already told you that phospholipids are amphipathic. Remember, they're double-sided. They have two different ends with two different functions. So one end, which is the phosphate end, and as you can see right there it says it, phosphate, that end is hydrophilic. So phospholipids are amphipathic. So phospholipids are amphipathic. They have one end which has a phosphate group. That makes it a hydrophilic. Of course, therefore it's polar. Okay, so that end is polar. And you can tell that that end is going to like water because it says it right there, hydrophilic, polar. Then the fatty acid part is nonpolar, therefore it's hydrophobic. Now that makes this phospholipid having a endedness to it. One end will face water, one end will face a fatty acid tail. So let's look at a picture. I guess I'm not having a picture yet, so I'll come back to that. So they'll show a picture of this in a little while. So phospholipids, amphipathic. They have a hydrophilic head with the phosphate group and a nonpolar with the hydrophobic tails, the fatty acid tails. Okay, we'll see a picture of that shortly. The next category is steroids. Now steroids are four-ringed structure, so you need to know that for the test. Steroids are four-ringed structures. So 4 rings. Now, steroids are animal-based. That means these are animal products. Okay, so these are animal products, animal-based. Cholesterol is your basic building block. Okay, so they're cholesterol. That's the basic building block of a steroid. So that sounds like a really good test question on a test. What is the basic building block of a steroid? It is cholesterol. And what shape will cholesterol take, or what shape will steroids take? 4 interlocking rings. So 4 interlocking rings are steroids, and cholesterol is your basic building block. And these are examples down here. Testosterone and estrogen would be, testosterone is the male steroid, estrogen is the female steroid. Okay, so these are examples of that. Okay, this category I told you I wasn't going to worry about. Okay, now this slide I do care. Vitamins A, D, E, K. I call it ADEC. Vitamins A, D, E, K. They are fat-soluble vitamins. You do not need to take too much of that. That's bad. So vitamins A, D, E, K are fat-soluble vitamins. That will be important for AMP1, but it comes back again to bite you in AMP2 if you didn't remember that. So vitamins A, D, E, K are fat-soluble vitamins. Okay, this is stuff I've already talked about. I already told you that saturated fats are single bonds. So saturated fats are single bonds. They are solids at room temperature. I already shared that. I also said unsaturated have at least a double bond in them, and they are liquid at room temperature. Okay, so that's important. Trans fats are partially hydrogenated, which makes it more of a saturated fat, which is bad for you. Okay, all right, now comes the categories of carbohydrates. Okay, carbohydrates. We have the monosaccharide, which is the simplest form, the disaccharide, and then the polysaccharide. Notice they are following the same structure, monomer, dimer, polymer. So you see the mono, the di, and the poly. So it follows the same structure, monomer, dimer, polymer. Now this formula is of value to you because that's how you're going to identify the carbohydrates. The ratio is 1 to 1. So the ratio for carbohydrates will be a 1 to 1. 1 carbon for every 2 hydrogens and 1 oxygen. That's what I mean by 1 to 1. 1 carbon for every 2 hydrogens and 1 oxygen. Okay, so you have your glucose, simplest form. It is what provides energy to the cells. So it provides energy to the cells. Very, very important. Then we have glycogen. Glycogen is a polymer. So glycogen is a polymer. Notice where it is stored. It's stored in the skeletal muscle. That must be very, very important for a future test. Okay. So let me backtrack in what I've said so far for this one. Glucose is your simplest form of carbohydrate. Then we have glycogen. Glycogen is a polymer. And as a polymer, it is going to be stored in the form of skeletal muscle. So your muscles have a lot of glycogen. So Lance Armstrong, the bicycle guy, he has a lot of muscle glycogen stored in his muscles for the Tour de France race. Okay? That's what I mean by this slide. I don't care for these two terms or these three terms down here as much. Here's an example. Here's glucose, a monomer. And as you can see, glycogen is a polymer made out of many, 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 many glucose molecules. Okay, so that's a glycogen. There are other forms of carbohydrates as well. So you have other isomers. Remember, isomer is when it has the same chemical formula, but it has a different structure, therefore it's different to the body. Okay, so that this slide is something to keep in mind. So you have other isomers. Okay, next slide. Then we have polysaccharides. Glycogen was already mentioned. Remember I said glycogen is stored in the muscle. Then we have starch. We have cellulose. Okay. So starch and cellulose are also a form of polysaccharide. So starch and cellulose, also a form of polysaccharide. Okay. We can't break down cellulose, but we can break down starch. So many of your crackers, for example, okay, your crackers have starch in them, so you can break down the starch. But you can't break down cellulose because we don't have the enzymes to do that. So that's why cellulose and starch look similar. Starch we can break down as humans. Cellulose we can't. A cow can, but we can't. Okay. So here are examples. There's galactose and fructose. And then we have ribose and deoxyribose when it comes to the DNA. And then we have sucrose, lactose, maltose. These are all sugars. They're all disaccharides, but they're chemically structured differently. So same chemical formula, but they're isomers because they're structurally different. Okay, then comes nucleic acids. Now this slide right here is the most commonly missed test question. This is the most commonly missed test question. The question is, what are the 3 parts of a nucleotide? So 3 parts of a nucleotide, when it comes to a DNA, the 3 parts of a nucleotide are sugar, which is a 5-carbon pentose, phosphate group, and a nitrogenous base. So here's the phosphate group, there's the nitrogenous base, and then there is the pentose sugar. In DNA, they call it DNA because it's deoxyribonucleic acid. It's missing an oxygen. That's why it's called deoxyribonucleic acid. And then for RNA, it's called ribonucleic acid. And that's the pentose sugar right there. And I say this is the most commonly missed question because what is the basic building block of DNA or RNA? The basic building block of DNA and RNA is a nucleotide. And what are the 3 parts of a nucleotide? The 5-carbon sugar, the phosphate group, and the nitrogenous base. And this is the most commonly missed question. Then, when it comes to the nitrogenous bases, we have two categories. Pyrimidines are made out of cytosine, uracil, and thymine. Okay. So pyrimidine is one group of nitrogenous bases. Now the way you're going to remember that is notice how pyrimidine is a very, very long word. It's a long word, therefore you're going to have to cut it. And you can see carefully why. C-U-T. That is your shortcut to remember that pyrimidines are from cut. Cytosine, uracil, thymine. Does that example now make sense? So if you've got this long word called pyrimidines, well, the way to remember that is you're going to have to cut it, and that's C-U-T. The other thing to remember is because it has a very long word, it's only going to have one ring. So if it has a long word, it's only one ring. Purines, on the other hand, purine is a shorter word, and therefore it's going to have two rings. So purines will have two rings, a double ring. Nimish, how will I remember this? Do you have a shortcut for this? Remember the word page. P-A-G-E. P stands for purine. A stands for adenine. G stands for guanine. And the E is extra just to remember the word page. Okay, that should help you there. So these are the 5 nitrogenous bases broken down into categories. The pyrimidines for C-U-T and purines, which are the A and the G. The shortcut I gave you a moment ago is of value for the test. Here's a picture version. So you can see pyrimidines all have a single ring. And the purines are only with double rings, right? So purines have double rings. You can also see that purines having all single rings are going to be the C, the U, and the T. And the purines will be the word page, adenine for A, G for guanine, and E for nothing. Now, you do need to remember this. Uracil is only found in RNA. So uracil is only found in RNA. And thymine is only found in DNA. So that's important. The other thing is the pairing. A will pair with T in DNA. So A will pair with T in DNA. A will pair with U in RNA. And G and C will always pair with each other regardless. Okay, so G and C will always pair with each other as usual. A will pair with U in RNA. A will pair with T in DNA. Okay, I've already shared this information. There it is at the bottom. A will pair with T. G will pair with C. And I've already shared that with you a moment ago. And remember, DNA does not have uracil. Only RNA has uracil. Okay, I've already shared that with you. Here's a picture version. RNA is typically single-stranded. So RNA is single-stranded. That's important to know. So RNA is single-stranded. DNA rather. DNA is double-stranded. As you can see that A will pair with T and G will pair with C. And the other thing you need to know for the test is this. A and T has 2 double bonds, which are hydrogen bonds. Let me correct myself. So A and T has 2 hydrogen bonds. G and C has 3 hydrogen bonds. They will ask that on a test. Okay. So let me rephrase all this one more time before I go further. RNA is typically single-stranded. So RNA is single-stranded. DNA is double-stranded. A would pair with T with 2 hydrogen bonds. G will pair with C with 3 hydrogen bonds. Okay. Next topic is ATP. So next topic is ATP. On this topic, I have this picture here. This is your adenosine part, and there's your triphosphate. Do you see these squiggly lines? If I remove that last phosphate group, I have now given something energy, and that is called phosphorylation. So if any of you have taken a general biology class, which technically should, but we're not doing that at HCC anymore, that prerequisite has been dropped. Not a good idea, by the way. But when you have a phosphate group attached to something, that's called phosphorylation. It gives it energy to do something. So when someone says, we take our glucose in our body and we convert glucose into ATP within the mitochondria. You may have heard of that. You're going to hear that later again in another chapter. So yes, the mitochondria's job is to eventually take glucose as energy and convert it to ATP. Well, where is the energy within ATP? It's in that last phosphate group. So that's how muscles will operate. We're going to attach a phosphate group to some part within the muscle, and then we're going to energize it with energy. And that's what phosphorylation is all about. It is the ability to attach a phosphate group to something and give it energy. So that's what we do. We take glucose that's in our body, we convert it to ATP within the mitochondria, and then that ATP, we take off the last phosphate group, we attach that last phosphate group to something, and we give it energy, and that's called phosphorylation. Okay, and that statement I gave you is important for a test. Okay, now we come to proteins. Now, unlike all of the other nutrients that I've mentioned, proteins will play the greatest role. As you can see from this slide, there are many, many functions that proteins will play. There is no way you're going to remember all of these functions. So that is why the shortcut I am providing to remember by is calling it multifunctional. And next to the word multifunctional, I'm going to use the English comparison called a verb. And as you know that a verb in English class is a action, right? So all of these can be converted to a action. Catalyze, defends, transports, supports, moves, regulates, stores. All of these words on the slide can be converted into a verb, an action. So anytime you see some form of action taking place in our body at any level, you know that it's going to be played by proteins. So let's take an example. I mentioned ATP in muscles a moment ago. Well, muscles are made out of proteins. So muscles will, since muscles are made out of proteins, muscles do move. And since muscles move, there you go. They're going to be made out of proteins. Okay? Do your blood, for example, your blood carries oxygen. So what do you think your red blood cells made out of? A protein. That's why they call it hemoglobin. The globin part is a protein because the globin part of your red blood cell carries oxygen. So anytime you have something that does something, think of it being done by a protein. That you will remember. Now you do need to know that proteins are made out of amino acids. So proteins are made out of amino acids. that you need to know. There are 20 known amino acids. So how do I get the millions and millions of different versions of proteins out there? Well, I get them from the 20 different possible combinations of these 20. Actually, not 20 combinations. I should say what? 20 to the 20th power. There you go. That's the more correct math. So it would be like 20 to the 20th power. And if you ever did that on a calculator, that's a huge number. So that's the number of different possible combinations I could have for the amino acids. So we have 20 known amino acids, and the combinations are like 20 to the 20th power. Huge. Now, each amino acid has two parts. One end of the amino acid is called the amino group. That's one end. So one end is called the amino group. The other end is called the carboxyl group. Now, are you noticing something here? I said that amino acids have two ends. One end is the amino group. The other end is the carboxyl group. So, Nimish, can we say that amino acids are amphipathic because they have two different ends with two different functions? Yes, you could. Yes, you could. Okay, next. Now, Nimish, you say that there are 20 different kinds of amino acids. What makes one different from the other? Well, the R group. The R group is different for the different 20 amino acids. So you have 20 different types of R groups, and that's how we get the 20 different amino acids. Okay. Now, when amino acids join with each other, they join to form peptide bonds. So when amino acids join, they join to form peptide bonds. Now, it doesn't say it here, but it's something I've already said. How do I join amino acids together? How do I join any form of nutrient together? Dehydration synthesis, by removing water. So that's why I said earlier, keep in mind that dehydration synthesis and hydrolysis are for all the nutrients. And in this example, peptide bonds will form. So for amino acids, peptide bonds form with dehydration synthesis by removing water. And it says it right there, formed during dehydration synthesis. Here's a picture version. So here's an amino acid. There's the amino group. There's the carboxyl group. And there's your R. And it's all going to be different for the different kinds of 20 different amino acids. How did I join to form a peptide bond? Well, I told you peptide bonds are joined together, and it forms what? It forms a dimer or a polymer or whatever, but it's done by dehydration synthesis, by removing the water. So here I have a very long chain of amino acids. No matter how long it is, this is important. No matter how long it is, one end will always be amino group. The other end will always be carboxyl group, no matter how long it is. So even if it's 1,000 units long, one end will be amino group. The other end will always be carboxyl group. Okay, now before I go any further, I have a long chain. These polypeptide chains, that's what they're really called. I know a lot of people just like to call it a protein, but it's really called a polypeptide chain. Now, for us, does it really matter whether you call it a polypeptide or a protein? Technically, for AMP1 or AMP2, it doesn't matter. But for general biology class, it would, because there is a technical difference between them. So here the author calls it polymer protein. He really should have called it polymer polypeptide. Okay, the polypeptide is what he should have called it. Now, Nimish, who decides how this chain is going to change shape and form something? Remember the rule I've taught you, that the shape, the anatomy, decides its physiology. So something is going to say, hey, how this chain right here on the picture there, picture C there, this polypeptide chain, something's going to say how this chain should change shape and form something. Now let's go back to a previous example from a previous chapter that I gave in my lecture video series. One of the questions or the comments I gave was sickle cell anemia, where in sickle cell anemia the red blood cell is distorted. It's sickle shape. And I just said to you that the red blood cell is made out of something called hemoglobin. And the globin is the protein part that's messed up in sickle cell anemia patients. Well, and I also said that in a previous video that because sickle cell anemia changes the shape and structure of the red blood cell, it carries less oxygen. Well, guess what happened here? Sickle cell anemia is a genetic disease, is it not? So because it's a genetic disease, it's the DNA that had gone wrong. The DNA is messed up, so it's giving the wrong kind of information on how to fold this protein to make a correct red blood cell, a correct hemoglobin. Same is true for the other example I shared at the same time in the previous lecture video chapter, and that was cystic fibrosis, where the mucus is plentiful of the wrong kind. Even that mucus is a protein that has been genetically screwed up. So in sickle cell anemia and in cystic fibrosis, the DNA of that patient decided how this protein would be messed up. And that's exactly what happens here too. It's the DNA that decides how the protein is going to change shape and form. That's important. Okay, don't care for this slide. Okay, this is a summary. It's nice to look at it, so just be aware of it's there. So when you're reviewing this video, make sure that you look at this nice summary. There's your phospholipid. That's that phospholipid bilayer. You see cholesterol right there. Remember I said cholesterol is a 4-ring structure, and you can see it now clearly. 1, 2, 3, 4. I couldn't show it to you before, but now I can. 1, 2, 3, 4. So cholesterol is your 4-ring structure that makes up your steroids. Notice you see it in the cell membrane. They sometimes ask that question. Do I see cholesterol in a cell membrane? The answer is yes. We also look at phospholipid. There's your polar head. The polar head being the phosphate ball. That ball right there is often called the phosphate group. So the polar head is because of the phosphate group. The non-polar tails are the fatty acid tails that can be either saturated or unsaturated that we spoke of. You can see how the directionality looks down here. This is the outside of the cell in gray. This is the inside of the cell in blue. And you can see that the phosphate heads are always facing the watery environment inside and the watery environment outside. That's why you see the phosphate heads facing outside and inside, whereas the fatty acid tails are facing each other because they are non-polar. They are oily. Okay, they are oily. Now, before I go any further, let me go ahead and ask a question that you should have learned before coming to me. This tells you something. It says that lipid things, now oily things, can do what? Oily things can go right through the cell membrane and end up inside the cell. So lipid soluble things can go right through because the cell membrane is like 80-90% what? Phospholipid, lipid. And like dissolves like, right? You learned that long ago. Like dissolves like. So oily things, fatty acid things, oily things, lipid things can go right through. But what about water? Water can make it up to here, and water can make it up to here, but water can't cross. So I need something called a channel. And there's a special channel for water that allows water to go through in and out. The name of that water channel is called aquaporins. Aquaporins. That's a water channel. they often ask for it about the general biology stuff. So aquaporin is the water channel that will allow water to go back and forth. You do not see that anywhere else. There's no other way water can get in. So there would be a water channel here called aquaporins to allow water through. Okay? And lipid soluble stuff can easily go through. So like vitamins A, D, E, K are fat soluble. They can go right into the cell. Okay, now we can move forward. So that's why this slide was a nice summary. Okay, here's a continuation of that same picture. Here's your DNA. Here are the protein parts. You can see a simple amino acid, and then you can see a polymer over here. Okay. I'm skipping all of these because I already talked about them. So this part I've already talked about. Don't care. These are the 20 known amino acids. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. The 20 known amino acids. Again, the difference is only in the white colored part, which is the R group. So everything in white is your R group. Okay. Again, we know that amino acids have a polar edge, which likes to go with water, and a non-polar part that likes to stick with the fatty acid part. So this is a repeat. Don't care, don't care. Now, this is where the DNA story a moment ago that I mentioned comes into play. That's why I mentioned it earlier. When you have a long chain, it's simply called a polypeptide sequence. So this is a polypeptide sequence. One end will be the amino group, the other end would be the carboxyl group. And that's your primary structure, the long necklace, the polypeptide. So polypeptide is primary. Then we have our secondary coming up. Again, I don't care about this slide. Don't care for that. Now comes the secondary level. Okay, so I skipped this slide I don't care for, and I skipped that slide I don't care for. Now I have the secondary level. The secondary level has two forms. The alpha helix, sometimes called a coil. So the alpha helix or coil, and the other is called the beta sheet, which looks like a folded sheet. Now, again, who is going to determine how I go from the primary, which is polypeptide, to the secondary, which is either going to be the alpha helix or the beta pleated sheet? Who decides that? The DNA. So the DNA will decide that. Okay, next slide. Then we have our tertiary, which I sometimes call intermediate. So some people call it tertiary, some people call it intermediate. Then we have the quaternary. Now this one has two examples you're going to need to know for a test. One is insulin, and the other is hemoglobin. And that's why you can see it right there, hemoglobin. So hemoglobin and insulin would be an example of quaternary. Now, as you can see, we went from primary, which was polypeptide. We went to secondary, which was alpha helix or beta pleated sheet. Then we went to tertiary or intermediate. And now we're on quaternary, which could be either hemoglobin or insulin. It's the DNA that decides how these foldings will take place. So the different level that you reach, level 1, level 2, level 3, level 4, the different levels you reach are based upon how the DNA codes for it. So if your DNA is coding for a messed up red blood cell, like in sickle cell anemia, then you have a problem. Now, what if I want to go the other way? What if I want to go from quaternary to tertiary to secondary to primary? What will happen if I go in the opposite direction? That is called denaturation. Denaturation. Let's take an example before I go any further. If you fry an egg in the morning to make your omelet, you fry the egg. You know that when you first put the egg in the skillet, you've got the clear runny part, and then you have the yellow yolk. The clear runny part is albumin. That's a protein. So the clear runny part is a protein, albumin. Then you have the yellow yolk, which is really the lipid, the fat. Now let's focus on that clear part. The clear albumin, when you fry the egg, it turns to white color, and it goes from more of a liquid, runny, clear thing to a more solid white thing. My question to you is, I want you to do it the other way. I want you to undo it. Take that fried egg, that white part of the egg that's been fried, and make it go back to clear, runny again. You can't, because you've already denatured the protein by frying it. So denaturation is basically going from a more complex structure to a more simple structure that you can't undo. So when you fry an egg, you've actually undone it by denaturation. So one way to denature a protein is heat or temperature. That's why I gave you the frying of the egg example. So one way to denature a protein is to heat it up to raise its temperature. The other way is to change the pH. That's why in the earlier chapters thing I mentioned pH. One way to denature it is by changing the pH. So let's take an example. In your mouth, we said that the pH was 6. That's what I mentioned previously. pH 6 in the mouth. So we have enzymes in the mouth that work at pH 6. But then once you swallow and it goes into your stomach, and I've already shared with you that the pH of the stomach is 2. So we're basically going from our mouth, pH 6, to stomach, which is pH 2. We are now going to turn off some of these enzymes by changing the pH from 6 all the way down to 2. Why? Because these enzymes are also made out of what? Proteins. Remember, enzymes do things. And since they do things and they are a verb, you know they're made out of proteins. So yes, you are denaturing enzymes or proteins by either heating them up, changing the temperature, and by changing the pH. Okay, moving on. So there's my word denaturation that I've been stressing to you. Notice what it says. It's a change in the protein. It disturbs what the protein does, so it messes it up. And notice it says it's usually irreversible, and it's done by either raising the temperature or by changing the pH. Very, very important for a test.